Put aside everything you think you know about the universe. You've been told it's a perfectly ordered place, a place where planets orbit stars in perfect harmony. But what if that's a lie? What if the universe is a broken, imperfect place, a place where unimaginable monsters are born from death? What you'll discover today contradicts everything you've learned from physics textbooks about the universe. Black holes aren't just giant cosmic vacuums, they're gateways to understanding the fundamental nature of reality itself. And recent discoveries have revealed that they behave in ways that challenge our basic understanding of space and time. This isn't just a topic about distant cosmic phenomena. The supermassive black hole at the center of our galaxy actively shapes the evolution of every star system, including our own. Without it, Earth might never have existed. By understanding these cosmic monsters, you'll grasp concepts that connect quantum mechanics to cosmic evolution, ancient light to the distant future of the universe, and the birth of galaxies to the ultimate destiny of all that exists. Imagine yourself standing in the heart of a giant star, surrounded by temperatures that would vaporize Earth in fractions of a second. Around you, nuclear fusion creates pressures equivalent to billions of atmospheres, while gravitational forces try to compress this stellar furnace into a point smaller than a marble. You are witnessing a cosmic war that has been raging for millions of years. On one side, you have nuclear fusion, a powerful outward-pushing force trying to blow the star to pieces. On the other, you have gravity, an inward-pulling force trying to crush it to nothingness. For millions, even billions of years, these two forces have been in perfect, delicate balance. But this balance cannot last forever. Our journey begins when gravity gains the upper hand. But how does the core of a star become so heavy that even light cannot escape? It begins with the life cycle of a star. A star like our Sun lives a relatively quiet life, slowly burning its hydrogen fuel over the course of 10 billion years. But a massive star, at least 10 times the size of our Sun, lives a short, violent, and ferocious life. This monster star burns its fuel at an incredible rate, producing heavier and heavier elements in its core. From helium to carbon, from neon to oxygen, from silicon to iron. Each stage of this process becomes more violent and shorter. The star is like a cosmic factory, producing the elements that eventually become planets and life itself. The calcium in your bones, the iron in your blood, the oxygen you breathe, they were all born in the hearts of dying stars. But iron is different. When a star reaches iron production, it reaches the end of the road. Iron cannot be fused to produce energy. In fact, it absorbs energy. At that moment, the star loses the ability to support its enormous weight. The battle is over. Gravity has won. In the final moments of a massive star's life, fusion ends. The star collapses under its own weight. Imagine the final moment. In less time than it takes light to travel from Earth to the Moon, a star 20 times the size of our Sun collapses from a mass larger than Mars to a point with no dimensions at all. The ensuing explosion releases more energy in seconds than our Sun will produce in its entire 10 billion year life. The outer layers of a star are violently ejected in an event known as a supernova. A magnificent, spectacular cosmic explosion that can outshine an entire galaxy. But the explosion isn't the most important part. What's left behind is what matters most. The core of a star collapses faster than thought. It shrinks beyond the size of a city, a house, an atom, until all its mass is compressed into a single, infinitely dense point. A point of zero volume. This singularity is called a singularity. That singularity is a black hole, but there's a barrier around it, an invisible sphere of influence from which nothing can ever return. Not a single photon of light. We call this the event horizon. The event horizon isn't a solid surface. It's a boundary in space-time itself. Imagine standing at the edge of a cosmic waterfall, but instead of falling water, It's the very fabric of reality bending and flowing inward at the speed of light. If you cross this line, there's no way back. This isn't because rocket engines are too weak, but because the direction outward no longer exists in the geometry of spacetime. A black hole is more than just a place, it's the end of space and time as we know them. Gravity becomes so intense that it doesn't just pull you in, it stretches you out, pulling your head and feet apart until your body becomes a long, thin string. This terrifying process scientists call spaghetti, or turning into spaghetti. But here's a secret most people don't know: the idea of black holes isn't new. The concept was first proposed in the 18th century by English geologist John Michell. He proposed that if an object is sufficiently dense, its escape velocity will be greater than the speed of light. However, it was a purely theoretical idea until Albert Einstein. Einstein's theory of general relativity provided the mathematical framework. It showed that gravity warps the fabric of spacetime. A massive object warps spacetime so much that it creates a cosmic hole. Then, in 1916, a brilliant German physicist named Karl Schwarzschild took Einstein's equations and, while serving in World War I, solved them. His mathematics showed that if you squeeze enough mass into a small enough space, you create a point of no return. He mathematically proved that black holes can exist. Unfortunately, Schwarzschild died of an illness a few months after his discovery, without seeing how his calculations would change our understanding of the universe. But wait, it gets more complicated. Scientists believe there are different types of black holes. The ones we've discussed so far, born from the death of stars, are called stellar mass black holes. They're relatively small, typically between 3 and 20 times the mass of the Sun. But they're not the biggest cosmic monsters out there. The universe has a much more powerful class of black holes. At the center of almost every galaxy, including our own Milky Way, is a supermassive black hole. These are enormous, with masses millions or even billions of times greater than our Sun. For years, scientists couldn't figure out what they were. Water explains how it became so big. Did it form from hundreds of tiny black holes merging together, or was it born differently? Science is still figuring this out. The supermassive black hole at the center of our galaxy, called Sagittarius asterisk, has a mass equivalent to 4 million suns. It's 26,000 light-years away, but its influence reaches every corner of our galaxy. Stars near the galactic center orbited at speeds of up to 7,000 kilometers per second. These astonishing speeds provide some of the best evidence for the existence of supermassive black holes. But what about other types? Could tiny black holes exist? The late, great physicist Stephen Hawking proposed that miniature black holes, called primordial black holes, could have formed in the first moments after the Big Bang. When the universe was incredibly dense and chaotic, these tiny black holes would be smaller than an atom, but would still have the mass of a mountain. But here's the crazy part. Hawking also theorized that black holes aren't completely black. Over vast periods of time, a faint glow of radiation, now known as Hawking radiation, emanates. It's the only way a black hole can lose mass, in a process that can take trillions of years. The black hole can eventually evaporate. Hawking radiation comes from the quantum properties of space itself. In quantum physics, even empty space is filled with energy fluctuations. Pairs of particles and antiparticles constantly appear and disappear near a black hole's event horizon. One of these particles can fall into the black hole while the other escapes. The escaping particle becomes Hawking radiation, and the black hole loses a little mass. This creates an interesting paradox. Smaller black holes have stronger Hawking radiation than larger ones. A black hole the mass of the Sun would take 1,067 years to evaporate, much longer than the current age of the universe. But a black hole the mass of a mountain would evaporate in a fraction of a second, producing an explosion more powerful than the largest hydrogen bombs. But what happens on the other side? If you cross the event horizon, is there a way out? According to general relativity, no. But this brings us to one of the biggest mysteries in physics, the information paradox. When something falls into a black hole, what happens to the information that created it? Is it truly lost forever? Or is it somehow encoded in the black hole's singularity? The idea of lost information violates a fundamental law of quantum mechanics. It's a debate that has pitted the greatest minds in physics against each other for decades. Some scientists believe that information is stored at the surface of the event horizon, in a principle called the holographic principle. Others suggest that the event horizon itself may be an illusion, and that information is emitted as Hawking radiation after a very long time. And what about wormholes? Could a black hole be a cosmic shortcut to another part of the universe, or even another universe entirely? While mathematically possible, physics suggests they would be incredibly unstable, collapsing instantly. No human, or even light, could pass through one. A wormhole would require exotic matter with negative energy properties to keep it open, and such matter has never been discovered. But what's even more intriguing is that black holes may hold keys to understanding the fundamental nature of reality. Some theories in modern physics suggest that black holes are linked to quantum mechanics in profound ways we don't yet fully understand. Quantum entanglement, where particles can be linked across vast distances, may be related to the geometry of spacetime around black holes. Today, scientists are still exploring these questions. Powerful telescopes like the Event Horizon Telescope have given us the first-ever image of a black hole, and gravitational wave observatories allow us to listen to the sounds of black holes merging, sending ripples through spacetime. The journey is far from over. In 2019, the world saw the first image of a black hole, the supermassive monster at the center of the M87 galaxy, 55 million light-years away. The image showed a ring of fire surrounded by a black shadow, just as Einstein's theory predicted a century ago. But what we didn't expect was the intricate detail in this image. The gases flowing around the black hole heat up to billions of degrees, glowing brighter than trillions of suns. This dancing material reveals the complex magnetic field around the black hole. Fields stronger than anything we can produce on Earth. These magnetic fields fire jets of particles at close to the speed of light. Jets that can stretch thousands of light-years across space. But even this amazing achievement raised more questions than it answered. How do these jets arise? How can black holes, which swallow everything, produce the most powerful jets in the universe? The answer lies in the rotation of the black hole itself. Most black holes rotate, and this rotation drags the fabric of spacetime with it in a phenomenon called frame drag. Matter orbiting a spinning black hole can extract energy from the black hole's own rotation, a process discovered theoretically decades ago but never directly observed until recently. This discovery has astonishing implications. If we can harness this process, we can extract enormous energy from black holes. A sufficiently advanced civilization could theoretically build cosmic machines around black holes, using them as power plants for stellar empires. This isn't science fiction. It's a direct deduction from Einstein's theory. But the most exciting discovery of gravitational waves came in 2015, when LIGO scientists first detected ripples in spacetime itself. This signal came from the merger of two black holes, each about 30 times the mass of the Sun, in a galaxy a billion light-years away. In a fraction of a second, this merger released more energy than all the stars in the visible universe combined. This energy wasn't released as light or heat, but rather as distortions in the fabric of space and time itself. These gravitational waves traveled through the universe at the speed of light, arriving on Earth as ripples so small they changed the length of the LIGO detector arm by 1/10,000th the width of a proton. Since that first detection, scientists have observed dozens of black hole mergers, each revealing new details about the nature of these mysterious objects. Some of these black holes are heavier than expected, others spin faster, and some merge in patterns that don't fit our current models. Most excitingly, we can now both see and hear the same events. When two black holes merged in 2017, the merger produced a powerful gamma-ray burst visible with conventional telescopes, while also producing the gravitational waves detected by LIGO. This gave us a three-dimensional perspective on the most violent events in the universe. But perhaps the most controversial discovery has come from studies of miniature black holes. Some scientists believe that primordial black holes, which formed in the early universe, may be a major component of dark matter, the mysterious substance that makes up 85% of all matter in the universe. If this is true, the universe is filled with tiny black holes that we cannot see directly. This theory is controversial because most models of primordial black hole formation require very special conditions in the early universe. But if it is correct, it would mean that black holes are not just rare accidents of stellar death, but a fundamental component of the structure of the universe itself. Now, some of the most fascinating questions in physics concern what happens inside a black hole. The conventional theory proposes that all matter collapses into a singularity, a point of infinite density where the laws of physics break down. But physicists suspect this cannot be true. Infinite density requires infinite energy, and this makes no physical sense. Alternatively, many scientists believe that quantum gravity, a theory we do not yet fully understand, would prevent the formation of a true singularity. The center of a black hole may be a region of incredibly dense matter, but not infinite density. This region may have strange properties, perhaps even connecting to other regions of the universe or other universes. Or perhaps black holes are not holes at all. Some theories suggest they are supercompression stars, objects so dense that they look like black holes from the outside, but lack a true event horizon. These hypothetical objects, called Planck stars or Boyle stars, would be made of matter in its densest possible state, so dense that a piece the size of a grain of rice would weigh more than the entire Earth. But what's truly fascinating is how black holes interact with the rest of the universe. When black holes swallow matter, it doesn't just disappear. The infalling matter produces intense radiation, and sometimes jets of high-energy particles. These processes make black holes among the brightest objects in the universe, a stunning contrast, completely black at their center, but surrounded by light brighter than trillions of stars. The gas and dust flowing toward the black hole forms what's called an accretion disk. Imagine a cosmic river of glowing matter swirling at incredible speed around the final gravitational sink. The material in this disk is accelerated to speeds approaching the speed of light and heated to temperatures thousands of times greater than the center of the sun. Friction between the different layers of material in the disk produces complex and changing magnetic fields. These fields can launch matter into narrow jets that travel thousands of light-years through space. At 99.9% of the speed of light, these jets are so powerful that they can influence the formation of stars in entire galaxies. And here we come to one of the deepest mysteries in modern astronomy. How did supermassive black holes form so rapidly in the early universe? Astronomers have observed black holes with the masses of billions of suns and galaxies that formed when the universe was less than 1 billion years old. But according to our current models, this is not enough time for small black holes to grow to such enormous sizes. This suggests that supermassive black holes may have formed directly in the early universe, without passing through the stellar black hole stage. Perhaps huge clouds of primordial gas collapsed directly into black holes with the masses of thousands or millions of suns. These early seeds can grow rapidly by devouring surrounding matter and merging with other black holes. But even more intriguing is the recent discovery of so-called wandering black holes. These are black holes that were ejected from the centers of their galaxies due to complex gravitational interactions, and now roam interstellar space at speeds of up to thousands of kilometers per second. The number of these wandering black holes in our galaxy may number in the millions, and they are virtually invisible unless they pass in front of a star or devour matter. What's even more alarming is that some of these wandering black holes may pass close to our solar system. A black hole with the mass of 10 suns passing within a light year of the sun could significantly distort the orbits of exoplanets. If it passed closer, it could knock Earth out of orbit entirely. Fortunately, space is vast, and the likelihood of a wandering black hole passing close to our solar system in the next billion years is extremely small. But scientists are watching the sky for signs of these hidden objects, using a technique called mini-gravitational lensing, which detects their presence when they pass in front of distant stars. Now, let's explore one of the most controversial theories in modern physics, the idea that black holes may be gateways to parallel universes. This idea comes from complex mathematical solutions to Einstein's equations called white holes. A white hole is the theoretical antithesis of a black hole. Instead of swallowing everything, a white hole spews matter and energy into space. The theory suggests that every black hole in our universe may be connected to a white hole in a parallel universe. The matter that what disappears into our black holes may emerge from white holes in other universes, and vice versa. This solves the information paradox. Information doesn't disappear. It just moves to another universe. But this theory faces significant problems. White holes would be extremely unstable in reality, and any small disturbance would instantly destroy them. We've never observed anything resembling a white hole in our universe. Although it should be very obvious, a continuous explosion of matter and energy from a single point in space. Alternatively, some physicists suggest that the Big Bang itself may be the white hole of a black hole in another universe. This idea, called black hole cosmology, proposes that each black hole creates a new universe inside it, and that our universe itself may be inside a black hole in an even larger universe. This leads us to profound questions about the nature of reality itself. If we live inside a black hole, what does that mean for our understanding of physics? How can we test this theory? The answers aren't clear, but scientists are searching for signs in diffuse cosmic radiation, the leftovers from the Big Bang, that may reveal the true nature of our universe. But perhaps the most interesting discovery in recent years has come from studying the way black holes affect light itself. When light passes close to a black hole, it is not only bent by the strong gravity, but its color also changes. Light emerging from the deep gravitational well loses energy and becomes redder, a phenomenon called gravitational redshift. This effect creates a fascinating phenomenon called black hole shadows. When we look at a black hole from a distance, we see a circular shadow surrounded by a ring of distorted light. This shadow is larger than the event horizon itself because it encompasses a region around the black hole where light is bent so strongly that it cannot reach us. The size and shape of this shadow contain amazing information about the properties of the black hole, its mass, spin, and electric charge, if any. Analysis of the shadow of the black hole M87* has revealed that it is rotating at a speed close to the theoretical maximum. Any faster rotation would destroy the event horizon and expose the singularity to the outside universe, violating the so-called cosmic censorship hypothesis. But what happens if a black hole rotates faster than this limit? The theory predicts the formation of a naked singularity, a region of infinite density exposed to the universe. This would be disastrous for physics, because a naked singularity could send signals from the future to the past, violating causality itself. Fortunately, we have never observed any evidence of naked singularities in nature. Now, let's talk about one of the most interesting practical applications of black hole physics, the possibility of using them as power sources. In 1977, physicist Roger Penrose proposed a theoretical method for extracting energy from a rotating black hole. The process, called the Penrose process, involves introducing an object into a special region around the black hole called the ergosphere, splitting it into two pieces, and allowing one of them to fall into the black hole. If done correctly, the escaping piece would carry more energy than the original object, extracting energy from the black hole's own rotation. An advanced civilization could theoretically build cosmic machines called Dyson spheres around black holes, exploiting this process to produce enormous amounts of energy. A black hole with the mass of 10 suns could, through the Penrose process, produce energy equivalent to converting 20% of its mass into pure energy. This is 10 times more efficient than nuclear fusion, and thousands of times more efficient than nuclear fission. A civilization capable of building such machines would have enough power to spin stars, reshape galaxies, and perhaps even travel through time. But using black holes as power sources raises interesting questions about cosmic balance. All the energy extracted comes from the black hole's rotation, which means the black hole gradually slows down. Eventually, a black hole completely depleted of its rotational energy would become a non-rotating black hole, or a Schwarzschild black hole, far less efficient at producing energy. This leads us to a deeper question. Is the universe optimized for intelligent life? The physical constants in our universe, from the strength of gravity to the mass of an electron, appear finely tuned to allow for the existence of stars, planets, and life. If these constants were even slightly different, atoms would not have formed, stars would not have ignited, and black holes would not have formed. Some scientists suggest this is no coincidence. Perhaps our universe is one of an infinite number of universes in a multiverse, each with different laws of physics. We exist in this universe because it is the only one among billions that allows our existence. Other universes may be filled only with black holes, or they may be completely devoid of any complex structure. But the multiverse theory is difficult to test, and some scientists find it unacceptable because it violates the principle of scientific flight. If it can't be tested, it's not science. Instead, they look for other explanations for adjusting the physical constants, perhaps in complete unified theories of physics, or in the properties of the early universe. Now, let's return to one of the most controversial questions in black hole physics. Can anything escape from inside an event horizon? For decades, the answer has been no, based on classical general relativity. But in recent years, some physicists have proposed quantum mechanisms that might allow information to escape from black holes. One such theory proposes that the event horizon isn't a real barrier, but rather an illusion created from our external perspective. From the perspective of someone falling into a black hole, they appear to cross the event horizon and continue toward the singularity. But from the perspective of an outside observer, the falling person appears to freeze at the event horizon and slowly disappear as Hawking radiation. This theory, called black hole complementation, resolves the information paradox in a radical way. No information actually falls into the black hole, rather, it is encoded on the surface of the event horizon and slowly released as Hawking radiation. This means that information is preserved, but retrieving it requires collecting and decoding the code for all the Hawking radiation emitted by a black hole over trillions of years. But another, more controversial theory proposes that the event horizon may actually be a firewall of high-density energy. According to this theory, anything attempting to cross the event horizon would be instantly destroyed by this firewall. This solves the information paradox in a simple way. No information can enter the black hole in the first place. But the firewall theory creates its own problems. It violates the equivalence principle, a fundamental tenet of general relativity, which states that free fall in a gravitational field is locally indistinguishable from floating in empty space. If there were a firewall at the event horizon, falling into a black hole would be very different from floating in empty space. Debates about these theories continue in the physics community, and there is still no consensus on which one is correct. Resolving this mystery may require an entirely new theory of quantum gravity, one that unifies general relativity and quantum mechanics in a consistent way. One of the leading candidates for this theory is string theory, which proposes that all fundamental particles are actually tiny vibrating strings in extra dimensions of space. In string theory, black holes have properties that are very different from classical general relativity. They may contain extended strings connecting them to other parts of the universe or even other universes. But string theory is difficult to test experimentally because the effects it predicts occur at energy scales far beyond our current technical capabilities. To test string theory directly, we would need a particle accelerator the size of the solar system, which is virtually impossible. Instead, scientists are looking for indirect effects of string theory on the behavior of black holes. If string theory is correct, Hawking radiation may contain subtle patterns that reveal the presence of extra dimensions. Observing these patterns would be powerful evidence in favor of string theory. The universe is full of mysteries, and a black hole is perhaps the greatest of them all. It is a cosmic monster born from the death of a star, a place where the laws of physics we know break down. An astonishing, terrifying, and astonishing phenomenon that forces us to question everything we thought we knew about space-time and the nature of reality itself. But this exploration of black holes has revealed more than just mysterious objects in space. It has revealed the profound interconnectedness between quantum mechanics and gravity. Between the smallest and largest scales of the universe, it has revealed that information itself may be preserved even in the most extreme environments, and that space and time may not be as fundamental as we thought. Each new discovery about black holes raises more questions than it answers. What happens to consciousness if it falls into a black hole? Can information travel backward through black holes? Are there advanced civilizations that use black holes as energy sources? Is our universe itself inside a supermassive black hole? These questions are pushing the boundaries of our understanding of reality itself. Every new telescope, every gravitational wave detector, every sophisticated computer simulation reveals more details about these astonishing cosmic monsters. In the coming years, new telescopes will uncover thousands of new black holes in our galaxy and beyond. Advanced gravitational wave detectors will allow us to hear black hole mergers from earlier eras of the universe. Perhaps one day we will develop the technologies to directly explore black holes, sending robotic probes to the frontiers of human knowledge. Black holes are not just objects in space. They are natural laboratories of extreme physics, windows into the deepest secrets of the universe. Studying them teaches us about the nature of matter, energy, space, and time. They force us to reconsider our most fundamental assumptions about reality. Perhaps most importantly, black holes remind us of our place in the vast universe. We are tiny beings on a tiny planet orbiting an ordinary star in a galaxy containing billions of stars. But our minds are capable of understanding and appreciating the wonders of the universe, from the smallest particles to the most massive black holes. This capacity to understand, question, and explore is what makes us human. As long as there are mysteries to solve in the universe, humans will continue to search for answers. driven by the same curiosity that led us to discover these amazing cosmic monsters we call black holes. The journey is far from over. Every answer leads to new questions. Every discovery reveals deeper mysteries. But that's the beauty of science and exploration. The journey itself is just as important as the destination. As we continue to explore the mysteries of black holes, we discover not just about the universe, but about ourselves and our place in this vast and amazing cosmos.